Okay, you've done stuff like that before. Now I quickly want to move to logistic regression and the goodness of faith for GLM. Give me 1 second. Okay, now I want to introduce you to binomial logistic regression. Of course, what we've done so far without um, exponential family. Okay, from the exponential family, when the response variable is categorical and it's followed by binomial distribution, we're able to investigate, we're able to show that binomial distribution is a member of exponential family, and we're able to derive the link function. Now, where do we use the link function? We use this link function in binomial logistic regression. Now, I want to welcome you to binomial logistic regression. Okay. Now, in the binomial logistic regression, when do we use binomial logistic regression? When the response variable is categorical. Let me tell you this. When the response variable is categorical, okay, using the conventional linear regression is not going to work. Okay. Number one, the prediction is going to be nonsensical because there's possibility you're actually going to have a prediction that go beyond a bound of 0, 1. Okay. And not only that, the relationship is no longer going to be linear. But how can we actually um, achieve a linearity? We know that when response variable is categorical, we're never going to have a linear relationship between that particular response variable and the systematic component. But what do we need to do to restore linearity? Why do we need linearity? We need linearity because so that we can benefit from linearity techniques of estimation. I'm going to say that again. Why do we need linearity? I said we need linearity. Oh, give me 1 second. I'm going to clean up this. I need you to pay attention. Okay. Please pay attention. Now, I said when the response variable is categorical, right? Using this, it's not going to work because we do not expect a linear relationship. There's not going to be a linear relationship between a categorical response and the systematic component. There's something need to be done. And what needs to be done? We need to have a way to transform the response. Do you know what we've done the other time? I told you on Wednesday, one of the benefits of a generalized linear model is that we do not necessarily need to transform the response variable, that we always do when there's a violation of assumption using a box cost transformation. But with the idea of, link function and the fact that the response variable is from exponential family, we're actually going to have the response variable transformed. Now, this is what happened. Because we've been able to show, because y follow binomial, and we're able to show that binomial is a member of exponential family. Don't forget, we derive the leaf function, which is a function of g of pi to be this, or to be log of odd ratio. Okay, now if I want to rewrite the logistic regression now, it's going to be log of this equal this. Look at that. The log of this equal that, which means we have restored the linear relationship. The linear relationship exists now between this and this. Does that make sense? So after you are able to obtain the link function, linearity exists. Now, when the linearity exists, then we can now benefit from using technique of estimation involving linearity. So that's exactly what I'm doing here. But let me tell you this. There are three forms of link functions when you are, you're dealing with the logistic regression. The common one is the logit that I call the log of odd ratio. We have another one that is called probit. We have another one that is called complementary log. Please, I need you to pay attention. I need you to pay attention. Okay. Now, let me tell you this. I'm going to tell you the difference between the three. And I'm also going to tell you the reason why we prefer the first one to the other two. Why what is common in statistical literature is the logit, which is the log of odd ratio. Now, in the log of odd ratio, okay, for us to be able to achieve this mathematically, for us to be able to achieve this, okay, there's a particular distribution that was used, which we call logistic distribution. Has anybody heard about logistic distribution? Okay, now logistic distribution. Okay, the f of x is this. Okay, where x lies a real number. Okay, and of course the CDF. Now, this particular function was used to achieve or bounded, situation where we want to restrict the scale to be 0, 1, because the when you are focusing on categorical response, we want the range to be in 0, 1. And instead of us to use this, because if you use this guy straight line, you're actually going to go over the range of 0, 1, and you're going to have a nonsensical. But instead, we use this that is actually going to show something like that. Sigmoid. Has anybody heard about sigmoid? Sigmoid function is an example. So we're using the CDF. We're using the CDF. So the essence of this, please pay attention. The essence of this is to convert. Let me tell you this. Initially, the variable was a categorical, and when you have a categorical response, linearity assumption fails. Okay, the categorical response is not expected to be linearly related to the systematic component. But what do we need to do? What we need to do is to convert the range, the probability range, to continuous scale. Logistic distribution enable us to achieve that. Logistic regression enable us to convert the scale, 0, 1 scale, into continuous scale. Because it is only when you have a continuous scale that you're going to have a linearity relationship. Does that make sense? Now, But you know what probit? The word probit is talking about. The probit actually use the inverse of a CDF of a standard normal distribution. The probit believe that, okay, if I want to convert categorical scale, okay, into continuous scale, then I will be assuming that the probability will come from a normal distribution, standard normal distribution. And that's why we're using, that. So whether to use a logit or a probit or a complementary log actually depend on, assumptions about the distribution of the error and where your probability come from. The third one that we call a complementary log, log. Okay, I'm going to explain that to you as well. The belief is that the way the range probability will be converted to continuous scale, it is believed that that probability is coming from an extreme distribution. Extreme value. Extreme value distribution that we call Gumbel distribution. Okay, the Gumbel distribution is this. Now take a look at that. The complementary log, we use that in survival analysis. Okay, because when you take a look at that, talking about the log of the negative log of survivor function. Log of the negative log of survivor function. Believe here is that the probability that we want to convert into continuous scale is believed to come from a Gumbel distribution. Now, logit and probit is symmetric, but the complementary log is asymmetric. Does that make sense? Okay, so that is, but the benefit of using logit, like I said, is a lot. And why it is common in statistical literature is because of interpretability. Okay, and that was what I said here. I think I said somewhere. Let me show you. Let me see. Yeah. Okay, here. Yeah. Can you see that? I said one of the main advantages offered by using a logistic regression model over a probit or log is interpretability of the regression coefficient in terms of odd ratio. That is one of the benefits. Okay, so now the one we're using now, please pay attention. If you don't understand, please ask question. The one we're using now, okay, is this one. You see question 2, the log of odd ratio. Do you know if we can solve for pi, if we have estimated regression parameter, solving for pi, that would lead us to equation 3. Can you see that? And if you look at equation 3, it's looking like equation 3 is looking like this. Do you know equation 3 is looking like this? You know how? Divide both sides by exponential, divide each of these in equation 3. Please pay attention. Divide by that. If you divide by that, what are you going to have up? 1 divided by 1 plus the other one would be raised to power negative. Does that make sense? So equation 3 here is equivalent to this. And that was why I said the other time logistic distribution was actually used. The CDF of logistic distribution. So equation 4 is in case you want to estimate the probability. What is the probability of somebody having a disease? That is a T curve. That's a pi curve. Or what is the probability that a customer that approach a bank will default? That is a pi curve. Okay. Now, and let me tell you this. We can also have a way to, if we have a log of odd ratio, if I take the exponentiation of the log of odd ratio, that will give me odd ratio, because it makes sense when we interpret in terms of odd ratio. And what do we mean by odd ratio? The odd ratio is just like the ratio of the probability of success to the probability of failure. That's odd ratio. That's all we mean. Okay. And I'm just giving an example here. When somebody bets 4 against 1, actually means you pay $4 for every $1 bet, and 4 against 1 horn means you pay $1. So I'm just trying to explain to you the way odd ratio work. But that is not where I'm going. I'm actually going to move. Okay. Now, when the response variable, like I said, is categorical, then that's where we consider logistic regression. For instance, if I am focusing on baby, whether a baby has a disease, a respiratory disease or not. Okay. When it does not have a disease, y equal to 0. That's just a labeling. When it has a disease, that's equal to 1. And I'm looking at the effect of gender. Effect of gender. What is the role of gender? Okay, in having a disease, a baby having a respiratory disease. Now, the gender is categorical, right? And of course, please, I need you to pay attention. We're getting there. We're really getting there. Now, of course, we are using this, right? You know how we got that, right? Okay, we derive the logit. That is the log of odd ratio, the link function the other time from the exponential family. Okay, and of course, we equate that to the mean. Okay, B0 plus B1S is the mean of the model. Does that make sense? Because the error, can you see the error? Error is not going to be there. Error equal to 0 because expected value of error equal to 0. So when you take a look at this now, we can actually interpret a pi here. Okay, we can interpret the pi here as the probability of having the disease, given the gender. And given the gender now, y of having the disease, I'm focusing on when y equal to 1, having the disease, given a gender x, gender x could be male or female. Any question on that? Okay, I'm interpreting now a simple binary logistic regression model. Now, I want to do this. If s equal to 0, please pay attention. S equal to 0 means I want to focus on male, right? S equal to 0, I want to focus on male. Now, what I'm going to do, focusing on male, it means I want to rewrite this now. I'm still focusing on somebody having the disease, but given is a male. Now, take a look at that. That will be pi 0. Okay? The probability of somebody having the disease, given that it's a male, okay? If I incorporate that, please pay attention. What is going to happen? My pi is going to be pi 0. Look at that. And when I plug in 0 here for s, what am I going to have? Beta naught. Is there anyone who doesn't understand how I got this one? Please pay attention. We're doing something theoretical here. I'm here now. What is that? Male equal to 0. When s equal to 0, I'm focusing on male, right? And that is going to be the log of odd. The log of odd is going to be equal to beta naught. Now, because the log of odd ratio may be difficult to interpret. Look at that, log of odd ratio. We are too mathematical. How can we make a log of odd ratio to be an odd ratio? Because odd ratio can be easily interpreted. What am I going to do? Mathematically, if I have a log and I want to remove a log, then I'm going to exponentiate. Does that make sense? Removing a log from here, you exponentiate the what you have on the other side. Then this guy now, exponential raised to power beta naught, now become odd ratio. It's no longer log odd. So that's going to be the odd, or odd of having disease for male. Don't forget that time I plug in s equal to 0 for that. So that is the log of having the disease for male. Can we also do the same and figure how the odd of having the disease for female? Yeah, that can be done. All what we just need to do, plug in s to be 1. Okay, we now want to move right now. Please pay attention. Okay, so what are we doing here now? What do you think we're doing here now? We want to find the probability of somebody having the disease, given that is a female. And in the nomenclature, we've labeled female as 1. So which means what I'm going to do now, I'm going to go back to the model, to logistic regression model again. Then I'm going to start plugging in. What am I plugging in? I'm plugging in 1 for X. When I do that, this is what I have here. But this time around, my pi, I'm going to call it pi 1 because I'm plugging in 1. The other time when I plug in 0, I call it pi 0. Please pay attention. Now, where we are now, that is going to take us to a different range. Now, look at where we are now. Can you see where we are now? Now, when you now see this, do you know that? Please pay attention. We can look at the difference. Please pay attention. We can look at the difference between when I consider male and when we consider female. And that, looking at the difference, is what we're doing here. Do you see that? What is the difference? The log of, odd ratio for female minus the one for male. And what's going to happen? It's more or less like I'm subtracting this guy from this guy here. What does that give me? That's going to give me beta 1. And let us make sense of beta 1. And let's make a mathematical sense too. Please pay attention. Matrix algebra is playing out. Focus on this. Another way to rewrite this is to write it in this form. Do you agree with me? The log A minus log B in mass is log A over B. Do you see that? And that is going to be the log of 2 different odd ratios. The one for male and the one, and what do we say we got the other time? We only got beta 1. Do you see that? We got beta 1. And let me tell you this. If beta 1, please pay attention. If you don't understand this question, please pay attention. Okay? Now, if beta 1, we've derived that all of that is going to be equal to beta 1. If beta 1 equal to the log of the odd ratio, the first odd, pi 1 over 1 minus pi 1 is the odd of having the disease, if female. Pi naught over 1 minus pi naught is the odd of having the disease, if male. The ratio of that, we have said we got a beta 1. Okay. Now, that is what we call the log odd ratio, the beta 1. But if I exponentiate the beta 1, I'm going to get odd ratio. Okay, please pay attention. What we're doing now is theoretical. Okay, pay attention. Now, we want to give it an interpretation. What did I say the other time? It is the log of odd ratio is a beta 1. But log of odd ratio will be difficult to interpret. But when we exponentiate that, it's going to be called odd ratio. And that is what I actually have here. Take a look at that. You see that? Exponentiation of beta 1 equal to odd ratio. Now I can give it an interpretation if I know the values of beta 1. If beta 1 equal to 0, okay, what does that mean? Exponential raised to power 0 is going to be 1. When odd ratio equal to 1, that is 50-50 for both male and female. And that was why I said it is equally likely to get the disease for male and female. That is when odd ratio equal to 1. Therefore, when odd ratio equal to 1, when odd ratio is greater than 1, when odd ratio is less than 1, it has a meaningful interpretation in statistics. Okay, now, what if in a situation now where the odd ratio is giving us 3? Please pay attention. If it's giving us 3, what do you have in the numerator? The 1 in the numerator is for female. Okay, now what I'm going to say now, I'm actually going to say it is 3 times more likely to get the disease for female, because female is in the numerator. Because having an odd ratio of 3 means 3 to 1. Does that make sense? Okay. Now, what if in a situation where the odd ratio is less than 1? Please pay attention. Odd ratio is less than 1. Like maybe we have 1/4. Okay. Now, if you have 1/4, okay, that will favor the one in the denominator. Which one is in the denominator? Male. Male is the denominator. Then you're going to say it is 4 times more likely to get the disease if male. I can still interpret this for female. Instead of me to say it is 4 times more likely to get the disease if female, I'm going to say it is 4 times less likely to get the disease if female. Does that make sense? So that is the interpretation. Okay. So the interpretation continues. Okay. This is another one. Please pay attention. Here we're still talking about disease, no disease. Here we're looking at the effect of age. And we actually have this model. And what is the probability that the baby has the disease if mother was S-year-old when the baby was born? Okay, please pay attention now. This is the model. Okay. Now, when you are considering age is not categorical. Age is continuous. What we can do is to consider if there's a unit increase in age. Now, when this one is actually focusing, when this is focusing for age S, then I'm going to consider another one that will be focusing on age X plus 1. If I have a unit increase in age. The other time that we did, the predator was categorical, gender. But right now, the predator is not categorical. The predator is continuous, age. Now, we're going to do the same again this time around where we plug in X plus 1. You know, this is with plugging X plus 1 to replace X. We're gonna subtract that from the log where we only have X, and by the time you simplify, we're getting beta 1 again. And getting beta 1, oh my God, math is easy. Math is easy now. Math is easy. Without math, there's no statistics. Take a look at what I have now. This guy can be written as that, right? Log A minus log B can be written as log A over B. And at the end of the day, if you take a look at what I got, okay, take a look at what I got, okay, okay, we're also going to arrive at odd ratio equal to exponentiation. Now, how do we interpret? Okay, the way we interpret it when the predator is categorical is different from the way we're going to interpret now when the predator is continuous. The predator is age. Now, how am I going to ask? I'm going to say ratio of odd of the disease for babies whose mom were S plus 1 year old when they were born versus those whose moms were X years old when they were born. Because I only consider X and X plus 1. Does that make sense? That is what that interpretation is talking about. And this is the odd ratio. And we can also have a situation where we're going to have more than one predator in a logistical regression. So I have how to do that in now, using this. Oh my God, my time is up. I'm actually going to stop right now and I'm going to continue from here after the spring break. Now, before you go, while you are on spring break, I will advise that you just take your time because we're going to be having midterm too very soon. Okay, watch my recordings. Enjoy your spring break and make sure you stay safe. Bye for now, everyone.